The product of a square number and a cube number is one of these options. Always a square and never a cube, always a cube, never a square, yada, 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 yada. Okay, I think the best way to figure this out is to, let n be a square and let m be a cube. But this means if we factor n, if we write the prime factorization of n, this will be p1 squared times everything up to pk squared. Well, that's not, hold on, that's not quite true. It'll be to powers of, it'll be even powers. I guess these primes don't have to be distinct. Let's put it that way. Although, okay, hold on. Let's do this a little bit better. P1 to the 2, K1, all the way up to PK2. Let's not use K. Let's go capital N to K capital N. And for M, if we write the prime factorization of M, we have Q1 all the way up to Q capital M, and we'll say this is 3 J1 and 3 JM, right? So n is a perfect square, m is a perfect cube, and that happens when each prime factor of this square appears an even number of times, and each prime factor of this appears a multiple of 3 number of times. So if I multiply these together, n times m, well, I'll write it like this. So obviously, if all the p's and q's are distinct, then this is neither a square nor a cube. We can probably, there's probably, now that I'm writing this all out and seeing how tedious it is, there's probably a better way of figuring this out. But if all of the p's are equal to all the q's, like if p1 equals q1 all the way up and pn is equal to qm, then if k is a multiple of 3, if each of the k's are multiples of 3 and each of the j's are even, then the product is still a cube and it's still a square. But that's not always going to be the case. So let's see if we can go through the options and figure out when things are and are not the case. So it's always a square number. This is false. Another way we could have done this question is just go through them one by one and come up with the counter examples. So A is false. So 8 is a product of a square and a cube, but it's not a square. So this can't be the right answer. B, always a cube and never a square. That's also false, because 4 is a product of a square and a cube, namely 4 and 1. And it's a square, but it's not a cube. So that's also false. C, sometimes a square and sometimes a cube. That's going to be true. Let me put that with my green mark, or pink mark, I guess. D, never a square, never a cube. Well, that's wrong, because never a square and never a cube. If I take like a square number cubed and a cube number squared. So what is a square? Well, 1 times 1. they didn't really leave out any of the trivial cases from these options. This is 1 is a square, it is a cube, so, and 1 times 1, there you go. Always a cube and always a square is obviously also false. So yeah, the answer here is C. You could do it by process of elimination like this, basically just coming up with counterexamples to everything, or understanding, when you write out the prime factorization and know how the exponents have to be either even or multiples of 3, you can just start constructing examples of things that satisfy each of these, or understanding that, well, sometimes when you combine all these exponents, sometimes they will all still be multiples of 3 or all still be even, but that's not always going to be the case. And so option C is the only one that's filled with, sometimes it works and sometimes it doesn't. So yeah, that's the answer. Not much more to say about this one. Thanks for watching.